So in the last class we talked about Poisson processes on the line, and in this class we're going to talk about its properties. So we have already seen one of its properties, which is perhaps the most basic one, which is if you take nt, so this is a function in the Cadeias functions of the positive real axis, then if it is distributed as a Poisson process with parameter lambda, then the probability that nt equals k is the same as the probability that a Poisson random variable with parameter lambda t is equal to k. So we have talked about this in the last class. We have proved this proposition. And in this class, what we're going to do is to prove more properties of the Poisson process in the line. We'll start defining an important function. It's a kind of shift. It's very similar to a shift, but it's slightly changed. It goes from the space of Cadeias functions to itself. And I will first write its definition, and then I'll explain what it does. So theta t takes a function n in the space of Cadeias functions and returns another function that when applied to a point S will give n of S plus t minus n of t. So let me show you in a picture what this function does. So you have here, we actually already used this function implicitly in the previous lecture. So we have here time. By the way, I'll describe time with another variable, maybe r, because t is going to be used in the theta t. So there's a t here, and our Cadeias function looks like this. It stays at 0, then it jumps to 1, then it jumps to 2, and so on. So what this map is doing, so if we apply theta t here, we are going to obtain another Cadeias function that I'll first draw and then I'll explain what it does. It stays a little bit in 0, then jump, and stays a bit more. So what is the correspondence between these points? So I'll mark here in purple, this point is this point here. So what I mean is essentially what theta does is it changes the axis to this new set of coordinates. So now we start from t. So when s is 0, we are at 0. So this is why the purple cross has y coordinate 0. When s is epsilon, we are looking at n of s plus epsilon, which is somewhere here, and we are subtracting n of t. And we continue following this function. So everything that you see here is going to be copied here. So that's what the function theta does. It's a kind of shift that not only acts in the x coordinate, which would be this term, but it also shifts the y coordinate by doing this. Okay, now that we have explained what theta does, we can state a lemma that uses we can state a lemma that uses theta in its definition, and it's going to be very important for us. It's going to be a main property of the Poisson process. So now we fix lambda, which will be the rate of the Poisson process, and some time t. N is going to be a Poisson process with parameter lambda. And now k is any number of points you want to observe, and a is a measurable event on the space of Cadillac functions. What this lemma says is the following. The probability of seeing this Poisson process at time t have n arrivals, so we are observing, k arrivals, we're observing exactly k arrivals, and then once we shift it, we see something. So back to our picture. Until time t, we had, for example, one arrival in this picture. So the probability that we see this one arrival. And in the future, we observe no matter what. We have some observation to do here in this future of the process. Is going to be equal to the probability that you observe exactly k visits until time t. So you're seeing some sort of independence here, times the probability that a fresh process sees a. So the number of observations here and what happens after is independent. So now we are going to show this, but later we're going to see many consequences of this lemma. So how do we prove this? So we first need to write n equals t in a more appropriate fashion. So let's rewrite the event we have. Nt equals k. This is what we need to rewrite. And theta the theta shift of n satisfies something. We are going to rewrite this first part as first, the kth arrival of the process has to be smaller or equal to t. Otherwise, we cannot have t arrivals at time t, k arrivals at time t. Moreover, the next arrival, tk plus 1, has to arrive after t. Otherwise, k would be larger, and t would be larger than k. So now we just replace this event by its equivalent definition, which is the intersection of these two. And we keep the theta t saying that something happens after time t. Now we are going to take the conditional expectation of this whole thing given tk, because this is something we know how to handle well. So now it's no longer probability, it's conditional expectation lambda. We keep the indicator function of tk smaller or equal to k to t because this is going to be measurable with respect to tk. We are conditioning on tk, so whatever depends on tk goes out of the conditional expectation. Now the rest is not measurable, it stays inside. We can rewrite this as, of course, its definition. Tk plus 1 is tk plus xk plus 1. And this is larger than t, and the theta is still here. Okay, we already did this trick previously, which is the substitution principle. I recommend everyone to review from Probability 1, which allows us to take, sorry, let me write this a bit more clearly, is a sum. Okay, so we can write this as follows. Let me get more space to the right here. We first write this as a function of a variable tk. Then we compose it with tk. This is just a definition of this strange notation here. And then we use the substitution principle to replace every occurrence of uppercase tk with lowercase tk. So this becomes lowercase tk plus xk plus 1, which we of course can also write as xk plus 1 is bigger than t minus tk. Okay, so now we have something here that we actually can reasonably well compute. The last step we're going to do is just to make it really clear that we can compute this conditional expectation, because let's rewrite what is not going to change from the above line. So here we have, here it's actually a probability rather than its expectation. I'm writing it as event. So here we have xk plus 1 bigger than t minus tk, and we are going to write this, sorry, belongs to A, right? We are going to rewrite this using the theta notation that we have introduced in the previous class. So first, let's recall what theta does. Theta takes a bunch of times, the inter-arrival times. So these are the x1, x2, x3 that give you the distance between each arrival. And what theta gives us is the function n that describes the number of arrivals until time t. So if we write this, how can we write this event in terms of the function theta? So for this we have to go back to the picture. So here in this picture we had tk here. This is tk. Actually, I'm going to even write as little as lowercase tk, because we did already this conditioning. And here we have tk plus xn plus 1, xk plus 1. So here what we have between this time and this time is x k plus 1 plus tk minus t, which we can also see as xk plus 1 minus t minus tk. This is important because this appears in the definition below. And now the other interarrivals, from this one to the next, this is just xk plus 2, xk plus 3, and so on. So here you see the exact formula that you have to plug in theta to get the future process. So this is x k plus 1 minus something that we know it's bigger than. So we're not putting anything negative on theta, thanks God. Xk plus 2, xk plus 3, and so on and so forth belong to A, given tk equals tk composed with tk. Okay, why is it good to write it as such? Because now we see exactly the independence, right? The tk's are not IID. The n is not independent from this. But now that we wrote everything in terms of theta, of gamma, sorry, we can extract all the independence. You see, here we are conditioning on something that depends on tk. And everything here inside is independent of tk. This is also independent of tk. So what we are going to get is the expectation of, with respect to the measure lambda here, tk smaller or equal to t, and then it's just the probability so let me say it like this. What is here inside is just how do I say this? Let me make a pause to, instead of going directly to the conclusion here, let me make another observation. Otherwise it will look like a big jump. This is the probability of some event A and some event B. So I'm calling this A and this B. Maybe A is not a good not good notation because A is already here. So let's call it C and D. Given something, and this we can write as the probability of the second one given these two information times the probability of C. Okay, so I can here we have an intersection. The intersection is different from the conditional by this extra probability. So if we put this probability underneath here, you can see the definition of conditional probability. So this fact is true for probability of simple events. It's also true for when you're dealing with the conditioning on something that looks like it has probability 0, but it still works. So one way to see that it still works is that this conditional probability on something that has probability 0 is a limit of normal conditionings when we use the Lebesgue derivative. Okay, so we have this equation, and here we have exactly that. So I'm going to write here the probability of D. So let's look at what D is. This is exactly this thing here. And you see that it's conditioned that tk equals little tk, and conditioned that the time of the next arrival is bigger than something. This random variable has exponential distribution because the exponential distribution has no memory. So given that this is larger than something, this minus this something is still an exponential random variable. So this probability here is exactly the probability that n belongs to A. Because we're going to replace this by something that still has exponential distribution and is independent of all the rest. So you see we are just taking theta of, gamma of several independent exponential random variables. So we are in the end just getting another Poisson process, and we are asking that it belongs to A. So here all we have is the probability of C. So the probability that x xk plus 1 is bigger than t minus tk, and here we have the tk equals tk composed with tk. And now we get this probability out. This just goes out of the expectation because it's a number. And this is the same thing we did again. So this is the probability that x plus tk is bigger than t given tk, or the conditional expectation if you want. And here we can put this inside again. We are just reverting everything that we did before. This is the expectation that, or the probability actually. Yeah, let's skip expectation. Tk smaller or equal than t, x plus tk bigger than t, and this is, sorry, I forgot the n in A, and this is the way we rewrote nt equals k. So we get exactly what we wanted. It becomes a product. So this this intersection turns into a product, and the product is removing this theta here. So this is a very nice statement saying that what happens, it's not everything that happens, but the number of arrivals that we obtain until time t is independent of what we see in the future. If we shift the future with theta, of course, if we know that there were 5 arrivals, this purple cross was going to be higher. But if we shift it down, pin it back to 0, what we see in the future here is independent of the number of arrivals until time n. And I said what happens before t is independent of what you see above this axis here. This is also true. We didn't prove it yet. We're going to prove it. We're going to prove that not only this silly event breaks like this, but we can replace this with richer events that see what happens until time t. And this will also break like this product. But this is the first step, and it's actually the main step to show that nt equals k decouples like such. Now we're going to see a corollary of this, which is perhaps the main corollary. And what this corollary tells us is that if we break time, let's set t0 equals 0. If we break time in a partition like this, t0, t1 until tj, and we count the inter-arrivals, so the probability that nt1 is equal k1, nt2 minus nt1 is k2, all the way to ntj. This is going to break into a product and not only it's a product, but here we get to just subtract time, tj minus tj minus 1, not ntj minus ntj minus 1, but ntj minus tj minus 1. So if you think this reminds you of something, good, because this is exactly what we saw for the Brownian motion. The distribution of the differences, the incremental differences of the Brownian motion breaks into a product as if everything was starting from 0 and running between times. And this is exactly what you get here. So this process here, the Poisson process, has independent increments just like the Brownian motion. It's just that it's a discrete process instead of continuous one. So how do we prove this? It's supposed to be easy, right? Because it's called a corollary. We take the event nt2 minus nt1, and sorry, it's supposed to start from nt1. nt1 minus nt0, I'll call t0 equals 0. nt2 minus nt1, and so on until ntj minus ntj minus 1. So this event, it can be rewritten sorry, what I wanted was exactly what I started writing. So here I want starting from nt2. Let me shift this here. This event is exactly nt2 minus t1 here, and you see that we are removing the extra n, and tj minus tj minus 1 as long as we compose it with theta t1. So let me make a picture to describe why this is true. So we have here a process. We are looking at the increments. So the increments so this is t1, t2. These numbers in time here, they are deterministic. They don't shift with time. They don't shift with the sample point. And we have the inter-arrivals. So here there was an arrival. Here there was another one. Here there were no more arrivals. So the increments you see here from T2 to T1, it's 1. This is NT2 minus NT1. Oh, sorry. What I should have done here is written everything in terms of T1. So here is T2 minus NT1. Here's Tj minus NT1. Everything should be subtracting NT1. So the next one we are looking again here. Let's put another jump and another time just to illustrate. Here's T4. T4 minus NT4 minus NT1 is this distance. And let us now shift our axis to be centered here, the vertical and the horizontal ones. And you see that all these heights that I drew here, this height, they are just the values of our shifted process evaluated at T3 minus T1, T4 minus T1, T2 minus T1. So this is why we can remove this thing here. Theta is taking care of this, but we have to shift time. So it's T2 minus T1 until Tj minus T1. Here is T1. Okay, so we have proved this equality of events. Now we can turn to our proof. We want to estimate the probability that NT1 is K1, NT2 minus NT1 is K2, NTJ minus NTJ minus 1 is Kj. So the first thing we do is to take this event that we're seeing here and writing it using the theta function, because we want to get it in a similar writing as the original event we had. But you see that here we are not always subtracting NT1. So what we are doing here is looking at the increments. But if we sum and subtract, oh, by the way, I just saw that I made a mistake here. This is not a bracket, this is a parenthesis. So this is all the vectors. The vector NT2, NT1, and all the way up to NTJ minus NT1. So here we have all these vectors are equal to these ones at the same time. So also their subtractions are the same. So if we are considering, for example, Tj minus 1, Ntj minus Ntj minus 1 is equal to Ntj minus Nt1 minus Ntj minus 1 minus Nt1. So in the end, the fact that this jumps here from 0 to n, these intervals here, can be written as a composition with theta, also gives that the inter-arrivals, the jump from here to here, can be written in terms of theta. So let me write it down and then we see why this is true. Nt1 equals K1. And here we have the vector nt2 minus t1, nt3 minus t1, sorry, minus t2, ntj minus tj minus 1 is equal to k2 kj. This event here composed with theta t1. So this is what I'm claiming, that we can rewrite this as below. We can use the subtractions that I mentioned here, or we can just go back to the picture and see why this is true. So this is the jump that the original process does from T2 to T1. Let's draw this in the picture. So here we have a process that makes several jumps. Here we have T1, and here we have T2. The first component of the vector, sorry, not this vector, the first component here is the number of jumps we do from this time to this time. So it's exactly this height here. Now, another thing we can look at is the theta t1. Theta t1 is shifting the axis to this new pair. And you see that now the jump is just n t2 minus t1. It's just n of this distance. Okay, first coordinate is correct. Second coordinate is nt3 minus nt2. So let's suppose, for example, that t3 is here. So that nt3 is equal to nt2 and the jump is 0. So sorry, this here there was a mistake here. This is nt3 minus nt2. Nope. Oh, sorry. Now I get what I did wrong. So this is nt3 minus t1 minus nt2 minus t1. Okay, now it's clear because nt3 minus t1 is exactly this height, because t3 minus t1 is this distance here. And then t2 minus t1 is this height, because t2 minus t1 is this distance. So in the end, we are getting 0, indeed. But now we have something that is composed with theta 1. So it's an event, I don't know, n belongs to A. I don't even want to write what A is, but we have exactly what we had in the previous lemma. So now we can write probability that nt1 is equal to k, probability that this event here happens. So nt2 minus t1, let us separate it, equals k2, nt3 minus minus t1 minus nt2 minus t1 equals k3, and so on until ntj minus minus t1 minus ntj minus 1 minus t1 equals kj. This is the event A. We don't have to, you just forget the shift theta. So you see, we just managed to pop this thing out of the probabilities and shift every time by t1. But we are in the same situation as we had before, just that all the times are shifted. So now we continue this and we we keep this first guy we already popped. And here we have nt2 minus t1 equals k2. And now we have all the rest joined together. This is going to be nt3 minus t2 minus nt2. Sorry, the first one is going to be minus t2, which is 0. So the first one is not a subtraction. You see, it's just one term. So this first term is going to be nt3 minus t2 equals k3. Then we have nt4 minus t2 minus nt3 minus t2 equals k4, and so on until ntj minus t2, ntj minus 1 minus t2 equals kj. And you continue popping everyone out by doing the same procedure until you get the product we have here, which is the product of the increments. And by the way, look at all these random variables here. They are just looking at the distribution of n at some time. So whenever we write, so we finish the proof of the corollary, right? But whenever we write ntl minus tl minus 1 equals kl in the above product, what we have is just the probability that a Poisson random variable with parameter lambda times tl minus 1 is equal to kl. That's all we've got. So in the end, the increments are independent and Poisson distributed. Just like in the case of the Brownian motion, the increments are independent and normal distributed. This is not a coincidence. There is a whole theory of what kind of processes can you break in such a way. Can you break it in independent things which have the same distribution? And there are two beautiful areas of probability that study this. The theory of infinitely divisible distributions, distributions that essentially allow you to do this, divide it infinitely many times as you want, and stable distributions, which are slightly different because you get something different when you divide. I cannot get into the details, but the relation that we see between this equation and the distribution of the increments of the Brownian motion is not a coincidence. There's a beautiful theory behind about processes that satisfy this. And although the Brownian motion and the Poisson process look like they have nothing in common, they are 2 points in a continuous family of things that can satisfy this equation. This is a beautiful theory that we are not going to cover. Now, what we're going to do next is to study what happens inside each of these intervals. So we're looking at the interval here, at the line here, and we're splitting it into intervals like this. So one thing we already know is that how the jump you do from one point of this to the other is independent. But we don't know if the points that we get here inside, like the jump times, let's mark them in a different color. So the jump times, can you get some information about what happens inside this interval by looking at the position of these jump times? Like if this jump time moves a bit to the right, does it change what information you have in this second interval? And another question, if I know that I have from T1 to T2, if I have 3 points, how are they distributed? Are they concentrated in the right? Are they concentrated in the left? Do they have some bias? So this is what we're going to study next. We already know what happens in terms of number of arrivals, but now we're going to study the location of these arrivals. And for this, we're going to study a bit the density of the arrival times T1, T2 that we use to define the Poisson process. So let's recall that under the law P lambda of a Poisson process with parameter lambda, the vector T1 all the way to Tk, it has a very well-known distribution. So, but this distribution is not easy to write because it's not independent. They are of course not independent because they are ordered. The way we do to understand their joint distribution is go to the interarrivals x1 to xk. So this is x1, x1 plus x2 until xk minus x1 plus xk. And xk's are distributed as a product of exponential lambda random variables. What does it mean in terms of the density of these random variables? Because the exponential distribution, it has a density. We can write the exponential distribution as lambda e to the minus lambda t dt for t larger or equal to 0. So we can write it as a density in a very nice way. And products of distributions that can be written as densities have a density. And the density is the product of the densities. So x, this distribution that we wrote here, the probability that x1 equals dx1. So this is a notation, kind of ugly notation for the density of the vector x1 to xk. This density is first indicator that all the x's are positive. x1 is bigger or equal to 0. Lambda e to the lambda x1 minus lambda x1. Indicator that x2 is positive. By the way, lambda e to the minus lambda x1, and the xk should be positive. Lambda e to the minus lambda xk. And we should have dx1 dxk. So on the space Rk, this vector x1 to xk has a distribution that has a density. This is the density. It's very explicit. And the fact that we have a density for x gives us the density of t actually. So let us see how this goes. What's the density given a time t? So we are given a k, a number of variables that we are observing. What's the density of t1, t2, all the way up to tk? So first of all, we should have the tk's ordered. Otherwise, this is 0. There's 0 probability that they are not ordered because they are sums of positive things. And here we have the difference between them playing the role in the distribution. So here we're going to get lambda to the k, e to the minus lambda t1. This is the distribution of the first variable. Now we get e to the minus x2, but x2 is t2 minus t1. And we can continue until lambda tk minus 1. So this is the distribution of the tk's written as a density. They do have a density in Rk. They are forced to be ordered, and they have this nice product structure as well. Now, the interesting thing is that we want to know how these points between T1 and T2. So let's start with a very simple example between 0 and T. So fix a positive T. We condition on NT being equal to K. So now we have something that definitely has K points, exactly K points in the interval. So we can talk about T1 and Tk as elements of 0t to the k and ask how they are distributed. That's what we want to do. And the reason why it's so nice to look at their density before conditioning is because densities behave well with respect to conditioning. So we're going to condition, but having the density, we know how to do it. The way we do it is, okay, you have a density, like here in the line, and you have an event you want to condition, for example, this event. What you do is you take the function under the graph, you take the indicator of the event you are conditioning on, so you kill everything outside, but you also divide by the probability of the event. It's like you do whenever you're conditioning. You intersect and divide by the probability. But intersecting is multiplying by the indicator function. So you're going to multiply by the indicator function here and see how this goes. So one interesting thing is that we can actually kind of calculate the probability of the event as well, because we have the density, right? So we can just integrate. But before we get to the actual calculation, you have to observe that nt equals k, which is the event that we are conditioning on here, it doesn't depend only on t1 to tk, which are the variables we are interested in. This is actually tk smaller or equal to t, and tk plus 1 is bigger than t. We have seen this already in the previous lemma. So it does involve the tk plus 1, but doesn't matter because we have the density for t1 up to whatever we want. So t row of t1 all the way up to tk plus 1, we know what it does. And we want to intersect with this event. I'm going to keep it writing like this, but I just wanted to motivate that we need tk plus 1. And we divide by the probability that nt equals k. So this is what we want to do in order to know the distribution of these variables here. So what's the distribution, what's the density that we already estimated? We calculated it's the indicator of the order until tk. And now since we are intersecting with big tk smaller or equal to t, we have to bound the little tk that we are integrating as well. And since tk plus 1 is bigger than t, we have to put tk plus 1 here. So we took care of this intersection. Now we have to remember what the formula was. We had the lambda to the k, e to the minus lambda t1, e to the minus lambda. So there are several of these until e to the minus lambda tk plus 1 minus tk. There was the probability in the denominator, which is the probability that a Poisson assumes value k. The parameter of the Poisson is lambda t to the k, e to the minus lambda t, and there's a k factorial that I'll put above because it was in the denominator. So this is the distribution. I wrote already, this is the distribution of this whole condition variables, but you see that I'm giving you the distribution with the tk plus 1 here, and we are not interested in tk plus 1. We had to use it because it's part of the conditioning, but since we don't want it, we can just integrate it out. So the distribution of t1 up to tk conditioned on having k points until time t is the integral of the above with respect to tk plus 1 from of the above. So the above is saying that we are integrating tk plus 1 from t to infinity. So this is taken care of by the limits of the integrals. The rest, the indicator function, stays 0 smaller than t1 all the way up to tk. This stays, and tk is more equal than t. Lambda to the k can go outside. K factorial can stay outside. Lambda t to the k can stay here. As well as, okay, I'm running out of space. Let us do it more cleanly. So we have lambda to the k over lambda t to the k. Good, some cancellation is gonna help us. And that's it. Oh, the k factorial. So this is what we have. And inside, there is also telescopic sum here helping us with cancellations. In the end, we're gonna only have, oh, by the way, here we have k plus 1 variables we are looking at. So this is k plus 1. So here we only remove k because we want another lambda here to help with the integration. So this doesn't depend on k plus 1, it can go outside as well. So the integral is actually here. And what's the integral of the exponential? Especially with this nice constant factor in front. Let's already do the cancellations here. Get k factorial over t to the k, e to the minus lambda t. And this integral is going to be exactly e to the minus lambda t, because it's where we're integrating from. And the lambda cancels because it goes down when we integrate the exponential. And we still have the indicator function of the order. T1 should be smaller than T2. All of them should be between 0 and T. Another nice cancellation, and you got a beautiful formula. Things should be ordered as we expect, and between 0 and T as we expect, and the density does not depend on any of the variables. This is fantastic. Doesn't depend on T1, T2 or anything. Just indicator of some prism, pyramid, some hyperpyramid, and some constant factor that make this exactly a density. So it integrates up to 1. Actually, why does it integrate up to 1? Because there are k factorial ways to order this. The cube has volume t to the k, so this is exactly what makes the integral be 1. We are picking just one of the permutations, but we are multiplying by the number of them, and we are dividing by the total volume of the cube. So what does this give us? So imagine that we're taking uniform random variables, u1 all the way up to uk, all distributed as uniform 0t random variables, and then we order them. We consider u1 tilde all the way up to uk tilde, and this is just the ordering of the UJs. So what's the distribution rho of u tilde 1 all the way up to u tilde k? So definitely there will be some indicator that they are ordered because we are requiring them to be. And intuitively speaking, I would like to say there should be a constant here. And the only constant that makes a probability is exactly this. But instead of using intuition, let's make something more explicit. You know that we can write this vector u tilde 1, u tilde k as the vector u sigma 1 up to u sigma k, where sigma is a permutation of 1 to n. Okay, but which permutation do we use? I don't know. Let's sum over all the permutations, but let's only keep this when they are in order. So u sigma 1 and u sigma k, they are in order. So now it's perfect. This is a now almost sure equality. That the ordered pair, we sum over all permutations and we just keep the one that keeps the right order, and we put the vector here of the permutation. So the nice thing about this is it gives us the density of these u's here. So what's the density of these guys? So we know the density of these guys. So the rho of u1 up to uk is indicator that all of them, they don't need to be in order, but all of them need to be between 0 and t. And then it's just 1 over t to the k. That's the distribution of the unordered pair. The distribution of the permuted sequence is for a fixed permutation, right? It's 0, smaller than u sigma 1. Don't need to be ordered here. Sigma k is more equal than t. And the same thing. So that the permutation does not change the distribution of the uniforms. But now, as we put this requirement that they are ordered when we define the distribution of the u tilde, we get that the distribution of the u tilde is going to be, of course, the ordering that is now very explicit here. Sorry, now it's really ordered. And when we have a given sigma, there is the probability that we are going to take the indicator function, you know, the density of u with that sigma. This is 1 over t to the k. So just copying the distribution of the original variables because they are the ones appearing here. But now, how many times can we get this? Because for every permutation, there is a different way to get this. There is a way to get the u tildes that you want. So if I want u tildes to be like certain vector, and I give a permutation, there is a way to choose the u's such that the permutation will be the u tildes. Exactly one way. So for each permutation, and there are k factorial of them, we can reach this using the original density here. So we just showed that the density of the u tilde is indeed the same density as the t conditioned on n equals k. So in the end, what we proved is that if n is a Poisson process with parameter lambda bigger than 0, and we fix t and k, so t larger than 0 and k bigger or equal to 0, the distribution, so we can actually define p tk as p lambda condition that nt equals k. So this is an event that has positive probability for every positive t and positive k and no negative k. So we can define this probability here. And what this theorem states is that t1 tk as a vector under p lambda tk has the same distribution of uniform random variables that have been ordered. So this is what we proved, and this turns out to answer our question. Like, we already know how many points we can find between T2 and T3. We know that it's a Poisson random variable with distribution T3 minus T2. We also know that this is independent from the other intervals around it, these joint intervals. Now what we're obtaining is also that given that you have 3 points here, I can just throw 3 uniform random variables, order them, and this ordered point will have the same distribution as the t's that fall inside that interval would have. So this is a beautiful result. And what we're going to do with this result is to do another construction of the Poisson process on the line. Using that, we know the increments are independent, and given the increment, we know the distribution of the points. So that's enough for us to construct the Poisson point process in the line again, using another construction that is not a sum of exponentials. And the advantage of the second construction is that it's going to be much more general. It's not going to use so much that we are inside the real line as the sum of exponentials did. So in the next class, we're going to give this next construction and generalize it to other processes that are not in the line. We're going to define Poisson processes elsewhere. So see you in the next class.